very good afternoon, gentlemen. I'm Girish. I'm representing BJ Technologies on digital radiography today. You just heard Mr. Rao. Almost he spoke about. He broke down the numbers: 1,800 per day, 1,600 per day, complete 100% radiography testing. And it hit me. Digital radiography. Why don't they do a digital radiography, and then at the last when he told about the digital radiography, about the ADR on ongoing online production with the manufacturing unit, with the cycle time, with the archiving the images and storing them for the longer time, all those stuff. So I'm going to talk about the fundamental of the X-ray on a digital radiography. We'll go with the introduction, casting and inspection, image enhancement, how the raw image can be enhanced with the filters, and automated inspection, how the systems are done for the casting industries on automobile parts, how the systems are automated with the robots, with the digital panel, with the conveyor, with the PLC programming, those stuff, and a little bit of welds and airbags, inflators, tires, and lastly about the computed tomography. The X-ray inspection is well established NDE technique in the automotive industry nowadays with the advanced technology. Interpretation of the image is done by trained human inspectors. It will be an easy task for the NDT. Say for example, the trained guy is an ASNT level 2 guy and he's interpreting the images. The thing he wants to know about, he's inspecting the casting part or the welding part, and a little bit knowledge on castings. We have a gas holes, we have shrinkages, we have porosities. So a basic knowledge why the porosity occurs, why the shrinkage, why the gas holes, and what type of welding, and is that the same type of defect in the weld. So if he gets to know the basic knowledge of the characteristics of the material or the weld, it will be easy for him to interpret the images. And about the growing trend automating the X-ray system process due to there are several factors also involved. The digital X-ray technology has introduced about in a large, medium, and small castings, production inspection with a high throughput, cycle time, 20 to 25 seconds, 25 to 30 seconds per part, from the loading to the rejection and acceptance level. Multiple angles. When it comes to the variation, the thickness variation of a part, which needs to be 100% radiographed. So with the multiple angles, the robot, the latest, the advanced technology with the robot programming, with the detector, they take the multiple angle shots, complex shapes, contour scanning, which involves the LDA maintaining the same thickness around the part. I'm showing the next slide, a frame which has a thickness where the LDA technology scans the entire image with the same thickness. And some of the examples I can give is like cross members, the engine blocks, the engine heads, control arms, and the knuckle joints. Now, if you see this is the LDA, this is the robot, and this is the robot which has an X-ray source. This has a LDA, and this is a frame where it scans the entire on a contour scanning, which gives the 100% inspection results. The contrast sensitivity can be achieved with the scanning. And this you can see an engine head where a 2D as well as the CT scanning can be done. And this is the casting inspection of a cross member of an engine head. If you look at the image, it's occurring the defects at the cross section. Now, when I talk about the image enhancement, the X-ray, when we take an image of a casting or any automobile or any part, we see a raw data. And when we see a raw data, there are some loss of data. So to enhance the image, we can have an automated defect enhancement filter, which the software applies the filter to make the image more enhanced. The contrast increases with the more grayscale values. You can see the comparison. You can see the defects. You see the difference when you enhance, when you apply the ADE. It's an example of a wheel system where the image is added with the ADE filter. These are the defects. And ADE plus noise reduction. So we have, in digital radiography, we have signal to noise ratio, contrast to noise ratio, and something we call as a spatial resolution. The detector, say that the automated machine runs for all 24/7, and we can have a periodic test on the detector after 1 week or 10 days to do the detector performance test and see whether the spatial resolution of the detector will pass or fail, because to achieve the 2% sensitivity on that particular detector, so periodically if you do continuing the spatial resolution test, this is the acquired image. You don't see much when it acquires, and when you apply the ADE filter, now you see the sensitivity, which wire we want to see. ADE plus noise reduction, we are reducing the noise. In the automotive industry, common to find 100% of manufactured parts required to be X-ray. Demands on the production of shipping schedule translate to inspection machines being operated 24/7. Increasing focus on quality of inspection. Yeah, when it comes to the customers or customers end, as Mr. Rao said, the quality plays very important. Now, the vendors or the customers says we need a better quality, or for the auditing purpose, or for the image. So increasing on the focus of the quality of inspection, quantity and uniform product evaluation. Faster inspection rates, inspection cost reduction. Fully automated X-ray image analysis is done by the computer. A automated X-ray system normally consists of a detector, a robot, where the programming is done. It's a conveyor based, where the image processing is done by the high-end computer machines. The image is acquired. The acquired image is sent to the ADR. So I can give an example, a knuckle joint. What happens is, forget about the customer end. Before we go to the customer end, a lab test is done in the lab, taking the part, and we see the 100% inspection is done on that particular part, which covers entire part. At the highest thickness, the greater thickness, we have an IQI to see the sensitivity at the higher thickness, whether we are able to achieve the sensitivity. And the positioning of the robot, the angling or the position of the robot. So a lab test is done, and then at the customer end, it is implemented at the same. So when the image is taken, the process should be so fast to maintain the cycle time. The image is taken and it's, say for example, a knuckle has a 5 views. If I can cover this knuckle, if I can cover this part in 5 views, so it takes the 5 views, the first software takes the 5 views, it stitches. So as soon as it starts stitching, the first view is sent to the ADR, and the ADR sees the defects, and the second and the third. So the ADR sees view by view a defect and then gives the result whether it is accepted or the failure. As I told you, the acquired image, the processing, the defect detection, the defect classification, even the classification. It's a level 2, it's a level 3, level 4. The phenomenal thing of an ADR, we can have a region of interest. The customer says, I'm not much worried about this region. My sensitivity, my more sensitive region of interest is this. Here, I need a level 2 needs to be accepted, and the level 3 defect needs to be rejected. So the ADR, to teach the ADR to play with the parameters, to play with the values, we need to tune the ADR in such a way that as per the customer's requirement, we can teach the ADR a level 2 is accepted at that particular region and the level 3 is accepted in that particular region. So the image processing, the defect detection, the defect classifications, defect evaluation, and the inspection result. ADR, the automated systems run on 3 modes: manual, semi-automatic, and the automatic. Manual, the operator or the NDT guy sees the image and he says, okay, this is the defect, this is the gas holes, this is the shrinkage, or he sees the defect and manually he press the button, this is a fail or this is the pass low. So no defects, I'll pass this. So this is the manual mode. This is semi-auto where operator ADR gives you the result. Okay, I found a defect. I'm failing this part. The operator thinks that no, I'll pass this part. So the decision again depends upon the operator, but the decision, the ADR also gives you the decision. Even the operators also think, no. If ADR is failing, I can pass this. Then he press the button, pass. Fully automated. The ADR, there is nothing to do with the operator. The fully automated, the ADR says this is the pass, this is the fail, and the automatic system runs on completely automated. So you can see some defects which is caught by the ADR. This is one of the automobile part. So these are the defects. The software has a predefined types of defects. So while tuning or while teaching the ADR, you can choose as a gas holes, porosities, shrinkage, even the foreign materials. These are some chassis frame on online conveyor, which is done by the LDA scanning, which is an automated part of a LDA, which runs on an LDA technology, scanning the 100% to see the defects in the weld. This is how the system looks like with a conveyor, with a robot. These are the results of the X-ray. Airbag inflators, for the safety, when the kit is bundled completely with the airbag, Now the X-ray can be done to see the placement of the airbag, absence or presence of the vent holes, even on the tires, the broken wire, the flayed wire out of tolerance, missing wires. These are some of the indications. The previous day, Mr. Wolf and Professor Krishnan Balasubramanian, right, and even Mr. Rao already brushed up with the CT technology, slicing. I have a 100 pages book. I do a 2D radiography. I get two-dimensional images. I don't know what is written in 58th page, 59th page, so I use a CT. It's a lovely technology. It slices the images and gives you the result. Okay, this is what on the 58th page I see the data. So we already know the technology. It's a three-dimensional, which can be used on a high energy rather than like 450 or 320, because we might get some artifacts, images on a 450 kV, if I'm not wrong, Mr. Wolf. And on a 3 MeV or the high energy, we get a very good results. This is how the transparency of a 3D image looks like. This is the defects. We have a rotating table which rotates, takes the image. The high energy CT engine head. And some micro CT relay part. So anything automated, automotive parts, not only about the castings, so that can be inspected through the X-ray using the digital radiography. As I told you earlier, we can reduce the time. Which the unit which runs on 24/7 manufacturing units, like 24/7 running, time consuming throughputs. And the best part is about the storage. The software is linked with the SQL database, where you can store up to 10 to 20 years all those images, and it has an annotation of who was the operator, what time, what date, what was the part, the serial number, all the data. Any questions you have regarding the ADR or?
For ADR, like if you are scanning some thick parts or dense metal parts,
Okay.
so there are chances that noise may occur in the image. So how it differentiates effect from a noise?
See, noise, that is what we do is, before sending it to the ADR, we take an image and see whether the captured image doesn't have noise. So we play around with the KV, we play around with the MA, and make sure we don't have a noise. The later images are sent to the ADR.
Then also there are some inherent scattering in
Yeah.
that part. There are some inherent noise that are.
Yeah, very minimal.
produced.
You get a very minimal.
So-
Like you can have play around with the values, which the software has a noise reduction values, which has the area filters, which we can reduce the noises.
Like even if we are getting noise, because I have faced something like this. In place of I mean there was a defect, but it was showing like a noise. It was a noise kind of thing, noisy part. It was a brass metal.
Okay.
So in that case, how we can differentiate between a defect, a genuine defect, and a noise?
Okay, with the
Because
noise and
in
without.
thicker part and high dense material part, there is an inherent sharpness. UP if I say.
Okay.
Total unsharpness.
Yeah, total unsharpness.
So inherent unsharpness is part of total unsharpness that cannot be reduced to some extent. So sometimes it may pick up a noisy signal as a defect, or a defect may appear as a noisy signal. So is there any, I mean, how it can correlate between a defect and a noise signal?
Okay, in that case, have you tried to check the grayscale values?
Yes,
When the
grayscale
noise
values
and,
are very good.
Okay.
Yes. The sharpness, I mean, contrast is also, it shows very good. I'm able to achieve the ratio also,
Okay.
the minimum maximum ratio, that also I'm able to achieve. But still, I'm getting some noise in that.
In the ADE and the ADR?
Fact. Sorry, in the
You mean to say on the ADR or on the captured image?
captured image.
You don't use the ADR?
No, we are not.
Just on the captured
Yes.
image?
I have used, I mean, there are some inherent filters also, I have applied
Okay.
those filters, then also I'm getting
Then
some
you also
sort
get
of
some noise.
Yes, so that is what I'm asking. In genuine noise, genuine defect signal, how it can differentiate the ADR.
Doctor, anything?
No, usually it's either shape, size, or contrast. These are the three types of characteristics that you use. Another factor is